is called problem solving.
And this could involve example 1D column. Okay. So you could have a soil column type problem. The head is given here. Head is given here. Okay, and the Q. The fundamental equation here is Q and keep in mind Q is equal to flux is basically minus K times dH by dx. Now you can get a whole bunch of variations with this problem. I might give you a head here, find the head here, give a flow, change the conductivity, or you might have a column with two different conductivities, and also V equal to Q by NE. You cannot see it? I can zoom it. Yeah, just tell me if you can't see something. Okay. Is that clear, Will? You are kind of my benchmark. Okay. Just shout L from there, okay? If you can't see anything. Okay. So that's kind of, and I can give a whole bunch of problems, okay? But keep in mind the conceptual model for horizontal flow systems is you basically somehow reduce the problem to this kind of one-dimensional situation, and then it will be a trick of finding given a head, finding flow, given a conductivity, finding the flow, or given the flow, finding conductivity. I can come up with a whole bunch of combinations. You can think about it, okay? And come up with a very realistic situation, but always conceptually it will reduce to something like this, okay? A good example is I can say, well, there is a regional confined aquifer. Say if I give you a problem like example, a confined aquifer is buried 100 meter below land surface. I'm just making up a problem. Can you read it still? Will? Okay. Thickness of the unit is 30 meters. A well located at the center of the aquifer recorded. I'm just making up this problem on the fly, so okay, and another well northern boundary here. In the flow how do you take an I made a problem like this and reduced it to a conceptual model. Can you draw a picture for me? I mean, this problem is basically a 1D problem, a silly 1D problem. You can't read the question at all? Okay. A confined aquifer is buried 100 meters below land surface. Okay. Thickness of the unit is 30 meters. A well is located at the center of the aquifer, and which recorded 120 meters of head. Okay. Another well is at the, let's change this, instead of northern, let me call eastern. That'll look a little better. Eastern boundary located along the center line, not along the center line, recorded 110 meters. Find the flow in the eastern direction. And this could be a problem like this. Think of, say I started drilling below this here, okay? So let's call, this is, I mean, the center is anywhere, right? So let's call this room is the center. So I started drilling from here, and I found there is a confined unit, okay? And I hit the confining unit at 100 meters below the land surface. So the unit confining layer from the ground surface is 100 meters, okay? And I kept drilling, and I found it's about 30 meters thick, so I obviously hit another confined unit, or confining layer at 130, so it's 30 meters, okay? Now the center is arbitrary, so I could say, well, this is my center, so wherever I started drilling, I found the head as 120 meters. And then I went along the center line in the eastern direction, so this is east. And head here is 110. Okay, now it's a trivial problem, right? So, yes? It's a trivial data, it's useless. So you might have excess data. Okay, in this particular problem, you really don't care. That you might typically find. I might give you a problem where there might be data, and there are some problems I may not give numbers. I might say, well, here's an aquifer which is a sandy unit, sandy formation, sand formation. Okay, and find something, and you might need a porosity, and I may not give you. Okay, and you should say, well, this problem needs porosity, so I'm going to assume it's about 40%. Okay. Yeah, I'm not given here. That's sorry. Okay. Yeah, I should give. Okay, that's a good location of the second well. So you say first well, okay, and then I can say drilling data indicated aquifer is a sandy unit. Does that close the problem? So this problem has got some fuzzy information, which I'm saying sandy unit, so you should assume conductivity somewhere between 1 to 100. So there is no unique answer in this problem. So you would say, well, since you gave Sandy unit, there is no conductivity given, so I'm going to assume it's about 50. Pick a number between, I mean, obviously you cannot pick 0.1 or very low number, or you can't pick a huge, very high number. Okay. So here's a case where I can come up with a question, pretty arbitrary question, but bottom line is it will reduce to a simple conceptual model and with some soft information or some excess information. And you should be smart enough to eliminate the excess information. You should be smart enough to take the soft information and come up with a number. Okay? Does that make sense? Okay. Now, in practice, you do the same thing. I mean, we might find a report which says the aquifer here is probably sandy aquifer, and you got to come up with estimation. Okay, so I would like you to kind of get a, so that's why you have to have a feel for conductivity values, you have to have a feel for porosity values. Okay. Of course, you'll have well logs, but you may not have the exact conductive information from the well log data. You might say, well, sand is here, clay is here. Have a permeability. You might have some porosity. You could have a gamma ray log, which might have some porosity, but it's still an estimate. I mean, it's not an exact value. Okay. Okay, so that's one type of problem. The second type of problem with horizontal pro is, I could say a filter. What's a typical car filter? 30 centimeters, no, 15 long. Radius is what, another maybe 5 centimeter radius. Okay. Inlet pressure is P1. Two. Some number, okay, I might give some number in terms of pressure, okay, and oil viscosity is some number. Find the here's a different application. It's just a, how do you do this? Okay, you know I'm talking about the car filter, okay, oil filter. So let's assume the oil filter is, in this case, installed horizontal. Okay, I'm going to say that it's installed horizontally. So you could have a horizontal filter. Okay. And the oil is flowing through the system. Okay. Now, since it's a different fluid, you got to use the formula. K is equal to, what is the formula we derived? I rho G mu. Okay, so I given you the viscosity, I will give intrinsic permeability. Ki, okay. So I might give a Ki, I might give you mu, which means you got to find oil permeability of the filter, right? It's no more hydraulic problem. Okay? But once you do that, it's a simple problem. Okay, I've given you the length, I've given you the radius. You should be able to find a flow rate. It's the same problem. Okay. Obviously, a real problem, I'll kind of think through it better and give you all the information. But I'm just giving you some few situations. Okay, so these are all horizontal flow approximation using Darcyslaw. Okay. Now the second set of problems could be vertical flow. Okay. A simple situation is just a vertical soil column. Okay. And I can say here is a soil column, and it's packed up to this length, say 3 meter. Okay. And so this is packed soil column, and it's got 1 meter of freeboard basically. Okay. And so it's dripping water here. Find Q. Okay. Given A. How do you do this? I'm going to give an area, so given the area, okay? Find Q for a given area A, okay? Now, how do you find Q in this system, like little q? The first thing is always to find little q, okay? How do I find little q in this system? Oh, an area and conductivity, of course, right? So let's pick some numbers. Say let's area equal to 2 meters squared, K equal to 10 meter per day. Can you find little q for me? What's the formula for Q? Q is equal to same thing, minus K dH by dx. Okay. In this case, we're going to have a z direction. So let's assume the z is positive this way. So this is equal to minus K dH by dz. Okay. And K is given 10. Okay. Times H1 minus H2 divided by delta Z, right? Which is equal to 10 times. What is H1? Let's assume this is the datum. What is H1? One? One? What do you say it's 1? What's the pressure there? Pressure is 0. So what is the definition of head? H equal to P by gamma plus Z. Okay? P equal to 0. Z equal to what? I'm sorry? 4? I assume datum here. Okay? Yeah, if you assume datum other way, it will still work out actually. You might want to check that. Okay? So I assume for convenience datum to be there, so it will be 0. So we'll actually come back and change the datum and see what happens, okay? So H1 is, it should be H2 minus H1, right? So okay, so let's say that gives me H1 equal to 0. Let's find H2. What is H2? What's the pressure there? What's the pressure head there? 1, exactly. Okay, at H2, P by gamma is equal to 1. What's the Z there? 3. Okay, so H is equal to 4. So H2 equal to 4. Sorry. Okay. So H1 equal to 0, H2 equal to 4. So 4 minus 0 divided by delta Z is H2, which is 3 minus 0. Okay. So you just do the math. That's the Q. That's the number. Oops. Okay, and once you find the Q, you could basically from that you can find A, because Q is equal to little q times A. It's a flux, and once you know the A, you know the flow rate. Okay, so you could clearly see I can play a lot of tricks here. I can put an oil instead of water here, which means you got to put a proper P by gamma. You should use the proper density to convert for the head. There's a lot of tricks you can play here in the vertical problems. Okay. Oh, sorry, I missed it. Oh, sorry, negative signs. Signs are very important. I made a mistake here. I already lost 2 points in this problem because remember there's a negative sign here. I have to carry the negative sign. I got to put the negative sign here. Okay. So I have to put the negative sign here. So let me put the negative sign here. So can you do this math? 10 times 40 by 3 is how much? 13 point something. Okay. So it will be negative 13.33. What's a unit? Okay. It might sound silly, but it's probably worth keep repeating that. Now, why is the negative sign? What does the negative sign say? It's not, don't think of downwards. It's basically, negative sign simply says it's opposite to the assumed coordinate direction. Okay. Okay. Now, what I would like you to do as a homework is reverse the coordinate direction. Assume your coordinate, as Steve said, has got some datum here, and then set it up, and you should get the same answer. Okay, but it will be a positive Q, which means it's along the direction you assume, the coordinate direction you assume. So this is a very subtle problem. Okay, so I might play some tricks. I could say, well, assume datum here. Okay, and so then the sign is really important. I want you to report not just 13.33, say minus 13.33, and then give a little bit of explanation. It's negative because it's opposite to my assumed coordinate direction. Because as you could clearly see, you might assume, I might assume datum here, and Steve might assume datum at the top. There's no way for me to grade and assess whether you understood the logic unless you report the direction properly and put a couple of notes saying that this is the reason for it. Okay? Okay, so this is a simple vertical flow problem. Now, I can make this problem a lot more interesting, saying that now this is a mundane problem because it's just a 1D column, right? So now I can come up with this problem like there is a let's say drilling indicator that there is a unconfined and hold on a second, sorry. Still uncomfortable using this, so I'll probably get better as I go along. And unconfined and confined Okay. What else? Okay. Let me make up this problem with give some meaningful numbers. Okay. Drillers found a acutard meter below ground. Okay. Further drilling indicated bedrock unit. Acutard is okay, and its thickness is, let's say, 1 meter. Okay. Okay. And piezo measurements in the lower confined unit indicated the head in the lower unit is let's say 30 meters. So okay, bedrock level. Find amount of water leaking acutard. Okay. The area is 10 kilometers squared. Now find the direction of flow. I probably should have prepared this before, but I just made up this problem. So hopefully it'll work. Let's see. Okay. I would like you guys to put this problem in terms of a conceptual model. Okay. and tell me how you would solve. And the clue is it's basically a silly vertical Darcyslaw problem. Okay, so you kind of got to go through these details and cut the information out and come up with a conceptual model, which is a simple vertical Darcy's law obligation. So can you draw a picture, and I'm going to ask one of the volunteers to come in and solve this problem for me. It's quite possible I might have missed some data, but I think it's okay. So if I have, just let me know. Ask. Okay. Let's draw a conceptual model for this problem, okay? The first thing is the driller is kind of drilling from the surface, so this is his ground, okay? And he started drilling and he found, first thing he did was he found a water table. And that is 3 meters below, okay? And then he keeps drilling and he found a little aquitard. Okay, and he hit that at 10 meters. Okay, and then he kept drilling and he found another rock, bedrock in it. And he hit that at 30 meters. Okay. So you already created a conceptual model here. Okay, you took all the information and drew a picture. That's what a conceptual model is all about. Okay. Now you got to really cut through the nonsense and find out what exactly I'm asking here. What am I asking here? What is boils down to what? How much water is leaking through this unit, right? So the focus is this aquitard. Okay. So if you want to think in terms of a one-dimensional problem, all I'm saying is, well, I could have given the same problem as here's a one-dimensional column, and the aquitard unit is how much? 1 meter. I think this is 1 meter. Okay. If I'm a nice guy, I would have given you, well, there is a 1 meter soil column, there is an inlet pressure, there is outlet pressure, find the flow through the system. And the area of the soil column is what? I gave you 25 kilometers squared. Okay? So from a planar area point of view, you're talking about a regional flow. So you're looking at a flow over a 25 kilometers square of aquifer. But as I said, if I'm a nice guy, I would have given you there's a one-dimensional column which is 1 meter long. The area of the column is 25 kilometers squared. There's an inlet pressure, outlet pressure. Find the flow through the system. As simple as that. But as being a professor, you don't do that. Okay, you want to torture the students, I guess. So you come up with this big story. But eventually, if you cut through the nonsense, it's basically a simple 1D column. So now the trick is to find the inlet and outlet pressure. What's the inlet pressure here? What's the H? And you could assume Z anywhere you want, basically, once you know this. the key is what's the pressure here? Let's assume Z is here, Z equals 0. I would assume this as a datum. Once I do that, I need to know head here and head here. What's the head here? 3. Okay, 7 plus 1, right? 8 meter. Okay, so H1 is equal to 8 meter. What is the H2? Okay, remember the second one said the guy installed a well here, and the water level in the well rose all the way to about 25 meters. So I really don't know exactly where it's 25. So it's somewhere, in fact, somewhere here, right? So that's the confined level.
It's 25 meters above the bedrock.
That's right. So this is the. So when I measured the head in the confined unit, I used rock as the datum. Okay. Now we got everything. So basically, the pressure here is, if I were to shift now remember, you could either use this as a datum or this as a datum. If you use this as a datum, then you got to subtract this distance, which is what is this? This turned out to be a pretty interesting problem, actually. 19 meters, right? Okay. So the inlet pressure is H2. So H2 is equal to, which is H2 is equal to 25 minus 19, which is equal to 6 meter. Is that right? Yeah. Okay. So now you can find the flow. So, but intuitively, where is the flow? Is it going from the confined to unconfined, or unconfined to confined? Confined to unconfined? Okay, Rohit says confined to unconfined. Any other answer? What do you think, Will? Hold. You had your chance. Okay, let's try someone else. Brian, what do you think? Which direction is the flow? Bottom to top, it's going from confined to unconfined. So you are agreeing with Rohit. Okay, 2 votes for confined. No, you got your chance. You had your chance. I'll come back. Okay, Steve. Okay. Okay, so 2 votes for this thing. Although one guy is kind of ready to reverse his vote, but we'll go with this. 2-1. Any other? Anybody wants to support unconfined to confined? Okay, Massimo. So there are 2 votes for. So the flow is going this way in one case, the flow is going other way in another case. And let's pick a tiebreaker. Who would be Richard? From top to bottom. Okay. Top to bottom appears to be the winner. Okay. Anybody wants to oppose that? Okay, Will is opposing bottom to top. Okay. Now tell me, Will, why do you think it's bottom to top? This is a very simple problem we just made up, which turned out to be a very interesting problem, actually. Why do you think it's bottom to top? Okay. Physically you're saying, okay, well, how much pressure it has in terms of energy? How much pressure the bottom has? 25 meter above bedrock, okay? Now if I shift my datum, well, let's do that, okay? I think the confusion comes from the bedrock, actually. Let's shift the datum to here now. Okay, let's say, okay. So based on, if I shift the datum here, H2 is equal to 25 meter. I don't have to mess around with that, right? And which is right, okay. Now based on this as a datum, what is H1? Well, it's simple, okay? Remember, guys, it's nothing but P by gamma plus Z. So don't always go back to the basics, okay? So H1, what's the elevation first? This is 19 meter plus 1 meter, 20 meter, right? So this is 20 meter. And P by gamma is the head at this point. What is the head at this point? 7 meter. So H1 is equal to 27 meter. Now will tell me which has got more pressure, which has got more energy. H1. So what should be the flow direction? Down. Now a conceptual way to look at it, what I would do is I will simply look at these piezometers. Okay? Look at, if I put a piezometer in the unconfined unit, it will go water level up to this. Okay? If I put it in the confined, it came here. Just by looking at it, I can tell which direction it is. Because that's a total head indicator, right? That's a total energy. Piezometer records the total energy, no matter what the datum is. Okay? The fact that this guy records a lower energy, lower total energy, it has to the other way around. Yes?
So if water came out of the
Oh, it doesn't even go out of the well. All I have to say is, I mean, that's why, as I said, I made up this problem. It happened to be an interesting problem. My original intention was to make it somewhere here. Okay? So if I simply said instead of at 25 meter, if it's at 29 meter, okay, then this water level would have risen up to this point, and then it's a recharging aquifer. Water will from the bottom to top if you do the math. Okay, so I mean, don't be fooled by, partly because all the conceptual model we have looked so far, the confined aquifer was charging into a unconfined system, which is the case in most of the time, okay? But it's not all the time. You could have a leaky unconfined system which is leaking water into the confined formation. You can have here's a good case. And this is very much a feasible situation. Okay, questions? Can you go back to that picture, please? I want to zoom it up. Oh, sorry, zoom it up a little bit so that you can. Okay, so the key is to draw a nice, this tells you how I can come up with this nasty English problem, but if you put it in terms of a conceptual model, it first of all lets you think through the problem a lot better. Okay, now here choosing the datum and direction is very important, because if you chose, in fact, if you systematically set up the coordinate system and don't even worry about the physics, there are several ways to solve this problem. One is to look in terms of physics. Just look at this and say, well, common sense says it has to go from high to low, and immediately guess. Okay. Now you don't have to do that. You can be a mathematician and say, look, I'm going to attack this problem systematically. Here's the datum, here's a coordinate system, and you'll automatically say your Q direction will come out correctly. Depending upon where you set up, it will be negative flow or a positive flow, and that should indicate to you which direction it is, even if you don't know this picture. Okay? So there are two ways to usually solve the problems, purely mathematical point of view and purely from a physics point of view. And I always prefer the physics better, because that's common sense approach most of the time. But as engineers, you should be able to do both. Okay? And hopefully every problem we solve, we'll try to attack from the both sides. Okay? Now I can make this complicated. I can have multiple units, 3-4 units, and they are interacting with each other. And I can make different fluid. Like I can say the confined aquifer has got a salty water in it. It's an ancient water which is salty. Okay? Now you got to compensate for P by gamma with the gamma of the fluid, which is the salt water. So the pressure is no more just, if you, the water raising in this piezometer is a salt water. Okay? So you got to compensate for the density difference. Okay? And there is an example in the book, I think, with saltwater system. But it's the same idea. You always go back and write the Bernoulli equation and put the numbers. If you think there is a different density, automatically put the proper density, it will work out. Okay? Questions? Okay. So this is a horizontal. Okay, so we looked at a horizontal way to solve the problem, vertical way to solve the problem. Then the last one is Darcy's law. In radial flow. Okay, this is an important application. Say, for example, in this case, I have a confined aquifer. So, okay, this is going to be my conceptual model for a confined aquifer all the time. Okay, a confined aquifer will have a top on the bottom, a top on the back. I mean, bottom and a top. I mean, and a top and a unit on the top. Okay, and then there will be a well which is screened fully, and the thickness will be B, and the head is always above the top unit. Okay, so this is a conceptual model for this is a standard conceptual model. Okay, so there will be a confining unit, top and bottom, and there's a thickness. Okay, and the head is always above, and there will always be a well. Okay, now in this case, let me start pumping from the system. Okay, so I'm going to extract water from the system. So let's say here's a confined unit. I'm going to sink a pump here, and I'm pumping. Well, I'm not going to. I'm going to pumping certain amount of flow. So that's the interest. Okay. So I started pumping in the system, and from a plan point of view, plan view, I can say this is a nice aquifer sitting in an island. Okay. Okay. So this is my island, and the well is right at the center. Okay, and that's a lovely island. Okay, and it's also a freshwater island. Okay, so let's assume there's an island sitting right there, and if you set the section, the island will look like this. Basically, it will have a confining unit running along all the way, and then okay, so this is my lake. Can you visualize that? So the lake is all around. Okay, so I'm going to start pumping in this aquifer. The minute I pumped, the head in the aquifer went down like this. Okay, so this is the pumped level. And let's assume steady state, pump level at steady state. Okay, let's put some numbers maybe. Okay, B is equal to 10 meter. This height is 2 meter, and the original height was say 5 meter. Okay, so it dropped from 5 meter height to 2 meter height level. Okay, and the water level in the lake. So if you go far away, the water level at the lake is somewhere very high, about 10 meter. Okay, so this is at the lake. Can you visualize this problem? So, well, it's a very simple problem. Okay, imagine a big cylinder. Okay, and I poked a hole in the center. Okay, at the extreme boundary, the head is 10 meter. From this is going to be our datum. Okay, 10 meter, and right at the center where I'm pumping out, the head is 2 meter. Okay. The question is how much water is coming through the well. Okay, and the well diameter is, say, let's assume it's about 30 centimeter. Oh, that's 15 centimeter. The radius of the well, centimeter. That's Let's assume it's a very small hole. It's 20 centimeter hole. How do I solve this problem? Can you see, first of all, the flow is no more a horizontal or a vertical flow, it's a radial flow. It's a radial flow. Okay? So in terms of conceptual model, I got it. I guess I got 10 more minutes, okay? So in terms of conceptual model, what we're going to have is, here's a well pumping, okay, from this aquifer, and the head here is 2 meter, and it's going to go back. Oh, sorry, this is at the lake. How much I said at the lake? No, let's call it as 5 meter. I'm going to change this. Sorry about that. Let's call that as at 5 meter. Okay. It has to be at the 5 meter, right? To start with, so it's the same level as the initial level. Okay. Because initially everything is horizontal. Okay. And the question is find Q. You can see that initially nothing has changed, so everything is flat. So whatever the lake level was should also be pretty much same in the aquifer. Okay, there is no flow through the system. And I start pumping, so I dropped my head from 5 meter to 2 meter here, but the lake would still remain. That's a free water body. Okay, so the question is, if I do that, how much water I pump through the system, and you should know how much is this distance. Let's assume this distance is 100 meters. The lake is 100 meters away. The radius of the island is 100 meters. Okay, so it's a radial problem where you got two concentric circles. This is the well, and this is my lake. And now the flow is like this. It's a radial flow into the system. So the first thing you need to do is you should apply Darcy's law in the radial direction, which is basically nothing but QR is equal to minus K dH by dr. And we'll derive this a little more formally in a couple of lectures from now. But it's basically, instead of applying the Cartesian direction, but other than that, everything is same. So QR is equal to minus K times H2 minus H1 divided by R2 minus R1. Okay. Now from the problem, you know, R1 is, how much I said, 10 centimeter. Okay. 10 centimeters, sorry. Okay. And R2 is 100 meter, and H1 is what? 2. Okay. And H2 is 5. All you do is just, then you find Q. Okay. Now the tricky part is, big Q is Q times A. What is A? What is A in this problem? Radius of the well? The radius cannot be A. I mean, so it's pi r squared? Small pi r squared? Okay. Okay, the answer is A is pi r squared. Pi r1 squared, right? So the answer 1 is A equal to pi r1 squared. Who says that's right? Or who says that is wrong? Okay, I'm going to hold on to you. I'm going to ask somebody else to give it a shot. Anjani. Okay, in this particular problem, we found Q, right? We just solved for Q. Okay, I can solve for Q. H2 is equal to what? 5. H1 is equal to 2. R2 is equal to 100. R1 is equal to 10 centimeter. Now I want to give, so everything is fixed here. I want to tell me what is the area. And Rohit told me it's pi times 5 centimeters squared, 10 centimeters squared. Is that right or wrong? Yes or no? Just intuitive. Feel free to be right or wrong. Don't worry about it. We could make mistakes and learn too. So, you lost your chance. Huh. No. What is the area? Is it pi r squared is correct or wrong? No, R1 is the smaller. He said R1 is equal to 10 centimeter. Quick, we don't have much time. Correct, right or wrong? Wrong. Why? What's the right answer? It should be the middle of the rectifier. So what he says is pi 10 times 50 meters squared, right? Oh no. What about this radius? Somewhere here? Oh, sorry. Somewhere here? No. Pick a number. Okay, that's there. Okay, that's the answer. Okay, he says pi times 50 meters squared, basically. Okay. Anything else? Steve. Okay, 100 meters squared. Okay. Well, first of all, keep certain things. Okay. Now, Rohit is wrong because he even violates the fundamental hypothesis. I told you flux is perpendicular to the area. Okay. He's talking about pi r squared, flux is this way. There is some problem there. Okay. So he just violates the fundamental principle. Flux is opposite to the area, horizontal to the area. Other two guys are okay because the areas they were talking about are perpendicular. Okay. Now the location is controversial. Okay. So Rohit is wrong basically from the definition of flux. Okay. Now what about the actual area? I'm going to just leave it open here. Okay. So when you guys come back, let's talk about it on Tuesday. Just think through this problem. You got to do this because there is a homework problem there. So you better think through this. Which area is the right area and why? In order to find the flow rate through the system. Of course, you can also read the book. We'll spend a lot of time on well flow. So if you in fact, the best way to learn in problems like this is by making mistakes. Because if you got the problem right for the first time, you don't learn anything. Okay. So that's the reason I like to get different opinion, not to show that you don't know the problem or anything, but by getting different opinion, we could find what are the possible mistakes we can make. Anybody wants to make a burning answer? So what is A? Pi r. Okay. Yeah, think through it. Okay. I'll tell you, this is all wrong. Okay. All these guys are, first of all, it cannot be the planar area. That's wrong because it fundamentally violates. So it has to be some sort of circumference. So you're going in the right direction. Okay. So, see, that's area. So you're looking at this shell, basically. Yeah. Exactly. This shell. Okay. So it is a circumference. And formula for circumference is not pi r, it's 2 pi r, by the way. Okay, so you got to go back and look into some of your geometry book, Will. Okay, but it's a circumference times something else too, and also where the circumference is. So why don't you think through it, and we'll come back. We'll talk about it this Tuesday.